Firmware Guy is going to present his overview.
What is SPI?
Of the
SPI is a
interface.
4-wire
That's
synchronous
the serial
interface.
peripheral
It has
interface.
4 signals: clock, 2 dedicated data lines, master out slave in and master in slave out, and a chip select. It supports full duplex operation, so data can flow between the master and slave simultaneously.
Firmware Guy
supports multiple slaves using separate chip selects, so that means each part you're trying to access has to have a separate chip select so it knows when to pay attention to the clock and data lines. It supports transfer rates from 1 to 20 megahertz depending on the underlying hardware. Also on this slide is a small block diagram that shows the direction of the signals and relative to the master and slave. By definition, the master controls clock, so no data can move in either direction without clock being present. All devices are also capable of receiving and transmitting data. Okay, this slide describes the 4 modes of SPI operation. Okay, so there's 2 parts that go into the modes. There's the clock polarity, so it's whether the leading edge of the pulse of the clock is either rising or falling. And then there's phase, so is the data valid at the leading edge of the pulse and changes at the trailing edge, or is it changing at the leading edge of the pulse and valid at the trailing edge? That is the big takeaway from this slide, is that when does the data change and when is the data valid? So once again, the clock polarity is what edge is it, a rising or falling edge clock? So clock polarity 0 is a rising edge startup clock, and clock polarity 1 is a falling edge startup clock. Then clock phase just tells you at what point is the data valid and what point is the data allowed to change. So if you hit phase 0, it's sampling off the leading edge of the clock, and if it's phase 1, it's sampling off the trailing edge of the clock. Okay, just to make things clear, I purchased L3G4200D Parallax eval little proto board. Unfortunately, because this board is laid out to support both I2C and SPI, they kind of renamed the signals, and you have to go into the spec to see this, but chip select is the same. They didn't rename that one. But MISO became SDI, MOSI became SDO, and clock became SPC. So just when you're trying to learn something, they throw in non-standard names. But this is the conversion. For the tricopter project, I've selected a basic 6-channel radio. I picked it up on Amazon for less than $100. It's a FlySky FS-T6. It's a basic radio, got fairly decent reviews. The first 4 channels represent the standard controls you'd think of on any RC plane. Roll, pitch, throttle, and yaw. There are 2 additional channels left. I haven't decided what I'm going to do with those. I'm sure I'll integrate them somehow. But the basics of an RC radio are, for each channel, it puts out a 1 to 2 millisecond pulse at a repeating interval of 18 to 20 milliseconds. And the pulse encodes the control output. So the width of a pulse translates to a particular control request depending on the channel and the pulse width and the width of the pulse. So here is an example from a logic analyzer of a read of the Who Am I register in the L3G4200D gyro chip. Now, the Who Am I register is very convenient, especially when you're trying to bring up the interface, because it returns a known value. So you can convince yourself that you have set the mode properly and are getting legitimate data. I've also added these orangish rust-colored lines to denote when the data was sampled. So you can see how I arrived at the value CF and how I arrived at the value D3 for each of these bytes. And then I summarize here per the data sheet. The CF translates to bit 7 equals 1, so it's a read-write, and a 1 happens to be a read. Bit 6 equals a 1 is MS. This enables auto-increment. My generic code always enables auto-increment whether I'm reading one register a bunch. There's no harm, no foul. And bits 0 through 5 equal to F. And that happens to be the base address of the Who Am I register in this part. The parts are generally organized as a series of registers. So using this offset as like this for F, you index into those registers. And the D3 is the value per the spec and what I received when reading the Who Am I register. This is another example of a single byte write to the gyro part via SPI. This happens to be a write to control register 1 with no incrementing address on this write. So basically what I've done is the 0F here in the second byte sets normal power mode and enables the XYZ axis gyros. So that's what this is trying to accomplish, but it's more of an example of a SPI write. So you can see the chip select, the clock, and the data going across. Where's the code? The code is not included in this episode, but will be in an episode that follows this. The code will take some time to go through because although it's very clear, it does support both an UNO and a 101 board, and for the UNO it supports both I2C and SPI. And I want to do another episode following this one that covers some of the design trade-offs and why I made some of the selections I'm going to make going forward. But there will be code available that presents I2C and SPI and using the Curie library for the 101. Thanks for watching my video. If you enjoyed my presentation and found it useful, please subscribe. All the examples that you will see and links to the current documentation can be found at www.firmwareguy.net.
Firmware Guy is going to present his overview